Module 5.1 Introduction to Phase Field Modeling. In this module, we're going to learn about phase field methods, theoretical foundation behind phase field, and how to apply this for mechanical engineering applications. In this particular submodule, we'll learn about the fundamental principles and equations that govern phase field, how to apply this for solving mechanical engineering problems, some of the capabilities and their limitation of phase field methods. And in the next one, we'll deal with some of the software applications as well. So the term phase here refers to a region within a material system that has uniform physical chemical properties. They are characterized by their distinct mechanical, thermal, and electrical properties. We will see this by an example very soon. So a phase field basically is a computational technique for modeling the evolution of microstructures in material based on the thermodynamics principles. And we want to predict the microstructural phenomena such as phase transformation, grain growth, and crack propagation. What are the applications for mechanical engineering? One of the most common cases for mechanical engineering application is crack propagation. We want to simulate the initiation and growth of a crack in materials to predict failure modes and improve material toughness. In that case, we can consider the broken phase as phi, order parameter 1, and the unbroken phase with phi, order parameter 0. Similarly, for grain growth, suppose a grain is being grown under some particular environment in experiments. In that case, we want to understand and optimize the microstructural evolution during thermal processing or growth to enhance the material properties. For example, a distinct phase field phi I with a particular grain can represent a particular grain growth phenomenon. Next, it can also be used for understanding phase transformations. We can study the transformations such as solidification, Martensite transformation, which is very important for steels, or precipitation hardening. And in that case, we can take phi equals to 0 for parent phase and phi as 1 for transformed phase. Let's discuss about some of the key principles of phase field. So as we saw in the previous slide, it's quite important to understand what is the order parameter. What is a way to distinguish different phases. So order parameter, as we said, is a field variable that distinguishes different phases, typically varies between values that represent distinct phases. So, and another key concept is free energy functional, and which might be quite challenging to determine as well. However, the free energy functional kind of guides the entire phase field simulation. The core of phase field model represents the system's total free energy, and this total free energy can be broken down into different contributions, such as bulk free energy. So if you want to understand what is the energy to the homogeneous part of the phase, what is the energy that comes from the gradient between one phase to another phase, and if there are any external fields, such as mechanical stress, magnetic field, electric field. So if you understand these three things, that is again, suppose there are two phases, if you understand the contribution of one phase versus other, we understand the gradient between one phase to another phase, and we understand the contribution from the external field, then we can formulate somehow the free energy functional of the phase field. Especially some of the common governing equations are Allen-Cahn and Hilliard equations. They describe the time evolution of order parameter based on minimization of the free energy. So I would note this term minimization of free energy accurately. This is kind of the case for most of the physical modeling processes anyway. And of course, it can also couple with other equations in physics, such as elasticity equation, heat transfer equation, and so on. And that can help us to model the interplay between the mechanical field and the microstructure evolution. So let's start this with an example. Suppose we have two phases, ice and air, and then we can consider a case where ice and air are quite distinct. In other way, the phase is uniquely determined by the value of conserved field variable. So C, which is the concentration here, is C1 in one phase, ice, or C2 completely air. So there's a 1-0 kind of determination. That is described by the Cahn-Hilliard equation, which is a fourth order partial differential equation on your slide. However, there could be cases where things are not so much black and white. So we can take ice and air and their interface. So remember, we talk about the bulk region, ice and air, and the interface region, which is the denoted by the cross section between ice and air on the right. The phase is not uniquely determined by the concentration, temperature, and pressure, but you have to define an order field variable, phi, and it is determined by a second order partial differential equation. So phi is order parameter, L and M are mobility coefficient, and F is the free energy functional. So what are the advantages of phase field simulation? So phase field allows to capture complex microstructural phenomenon like phase transformation, grain growth, crack propagation in very details. It's very versatile. It's applicable to a wide range of materials, whether it's metal, ceramics, polymer. It can handle complex topologies. So it can topological changes such as merging, division, or dissolution of phases can be captured using phase field. Given if you know the, of course, the functional form. And also coupling with other physical phenomenon can be integrated with other physical models as well. However, there are several challenges, very similar to what we saw in the coarse graining technique, going from atomistic to coarse graining technique. You can see here, it requires significant computational resources, especially if you have 3D simulation. And the parameters are very sensitive for a particular model. So the model outcomes can be highly sensitive of the value of input parameters, which may need precise calibration from experiments or higher fidelity simulation. So this is not really ab initio type simulation. Also, scale bridging can be an issue. So while effective, a certain scale bridging behavior observed at the nano or atomistic level to macroscopic property can be challenging because it lacks the atomistic description. Also, model complexity. So develop and implement phase field requires a hardcore knowledge of a subject matter and the numerical method. So that also kind of poses a challenge for implementing phase field simulation.